Great, so hi guys, my name is Milind and I'm a senior here, and this is Jim.
I'm Jim Ostrowski, a mentor with the 971 team. Milind's going to take it over, so I'm going to step off frame until the very end.
Yeah, so we're going to be discussing our vision for our 2022 robot, and you'll come to see how really this is super vital for our robot's performance in shooting. So why do we need vision, first of all? One of the things is we need to know where we are on the field. We need to know that primarily for shooting, but also for autonomous, we need to know where to drive. And we also need to know how to aim at the goal. So there's an angle, like horizontal angle, that we need to figure out. And we also need to figure out how hard do we need to shoot the ball to go into the goal. And we need to localize and figure out where the target is so that we can aim at it. And as you see in the bottom here, this is our robot running its autonomous at SVR. And the reason it's able to shoot so well and move in an accurate path is primarily because of vision. Because we have other methods like drivetrain encoders and IMU, which also help tell us where we are. However, those only work on short time periods, and they start to get a little less reliable. And we need vision to really seed our location of where the robot is. Yeah, so our robot has 4 Raspberry Pis, which are basically mini computers. And they are each angled at 90 degrees away from each other. So this gives us a 360-degree field of view because each Raspberry Pi has a camera which can see 90 degrees. So no matter where we are on the field, the idea is that we are able to see the target and we can figure out where we are. Phil?
Is it exactly 90 degrees, or do you have a little bit of overlap?
It's a little bit of overlap. It's not exactly 90 degrees,
okay.
But it's pretty close.
Okay,
yeah.
Cool.
And yeah, so each Raspberry Pi has a camera, and our electrical team has made custom LED boards that shine really, really bright at the target, so we can see the reflective tape on it. On the top of the hub, there's like reflective tape around. And each Raspberry Pi has its own vision process that processes the camera information from its camera and then figures out where that camera is located, assuming it can see the target. And then we will eventually fuse all the Pi's estimates together to figure out where the robot is. And yeah.
How do you do the centrifusion?
Oh, sorry, what?
How do you do the centrifusion?
Oh, yeah, so we will get to that in another talk. It's about localization.
Okay.
But yeah. So. And our code is, all of this code is in C++. Yeah. And so this is our LED board that the electrical team made. And these are our Raspberry Pis. So you can see there's one Raspberry Pi with the camera and LED board here, the robot, and then there's a few others there. We have 4 total. Yeah, Phil?
I don't know if it's common knowledge, but I believe all the code is available on GitHub. Right?
Yeah. So all of our code is open source. You can go to GitHub, and I can share the link after the presentation if you guys are interested. Yeah, so basically an overview of the whole vision process. First, we just grab a picture of the hub or whatever the camera is seeing. And this is a process per Pi. So each Raspberry Pi is running this process. Then in the picture that we captured, we're going to look for green because we're shining this bright green light at the reflective tape on the hub. So we're just going to filter everything that's not green. Then we're going to detect these like blobs of reflective tape in our image. But however, we might detect some noise. Like let's suppose there's something else that's green in the image. We might detect that, so we then have to filter that out. And after we've found the pieces of tape, we're going to figure out, compute actually how far is the target and what's the angle. And eventually, we're going to send these results to the centrifusion part, the localizer, which is going to figure out where the robot is. So we're going to go over each step of these right now.
Are you going to be able to share a link to this presentation?
Yeah, definitely. Yeah. So our first step is just to grab a picture. So we use low exposure on our camera, which means that the time that it gets photons for each image is less. And that means that we get really intense sources show up much brighter. And the reflective tape, when we shine this green light at it, comes out super bright, and everything else is basically really dimmed out. This is in a daytime, but the image looks like it's at night, and we can just see these reflective tape, and that makes it really easy for us to figure out just find these pieces of tape. And we use a library called V4L2, which supports real-time capture on Linux. so we can just take images in our real-time system. Our vision code is not completely real-time if you know what that means, but we use this. So all of the images of the target will look something like this, and now we have to actually find these pieces of tape. So now that we've taken the image, we're going to convert this. This image is RGB. It has a red, green, and blue value for every pixel. Technically, it's a BGR because we use OpenCV, but you can ignore that if you don't know what that means. And we convert this to what's called a binary mask. So basically, every pixel that we consider green is going to become white in this binary mask, or the value will be 255. And every other pixel that we don't consider green will just become black. And we go through the whole image, every single pixel in it, and we check that there is more green than blue and red in that pixel. Because like if you look at this green, right, it shouldn't have much blue or red. It should just be green. So that's how we're going to filter it to that. So now that we've filtered the color and we see our binary mask, we need to actually detect these pieces of tape. So OpenCV has a function to find contours, or like each one of these is going to be a contour, and each one of these pieces of noise here is going to be a contour as well. And now we could have some issues, right? So maybe suppose there was like a partial blob here. Like suppose this piece of tape was split into two, and we didn't detect a whole one. We actually do another step, which is filling in these broken up pieces, so that we don't detect broken pieces of tape, because that would seriously mess up our detections. And then, so once we found each piece or contour, we're going to detect some statistics about it. So the first thing is the centroid, which is just the center point of it. So we'll get the center point for each one of these and each one of these. And then we're going to take the size of so each rotated rectangle is basically, if you fit a rectangle around this shape, you would get a rotated rectangle. So it might be tilted slightly upwards to fit this contour, and it would just be bounding around this whole shape. And we would do that. We would find a rotated rectangle for each one of these, and then we're going to figure out what the size of that is. And that basically tells us how big each of these contours is. And then we're also going to find the aspect ratio of it. So the aspect ratio, we know that the aspect ratio of the actual tape pieces is 5:2, and eventually we're going to use that to check that these have a similar aspect ratio, which means basically the ratio of width to height of each rectangle. Now we also compute the area of these blobs. So that's just how many pixels are inside it. And we're computing all these size statistics just basically to filter out small blobs that are not actual tape pieces. And the last thing we compute is the number of vertices. So if you put a shape around these, for some of them maybe it's just it just has 4 points, but if we had more complex shapes, it might go to like 6. Or if we had small points here, they might have like 2 vertices if you drew like a line through them or something like that. And we just want to make sure that that it's not too small, again, so we can filter out these pieces of noise on the side. Does that make sense to everyone? Okay. So now that we have all these statistics on each one of these, we want to actually filter them out. So yeah, we need to filter out the small pieces. And so we're going to use the aspect ratio because, as I said, the actual tape, the width to height ratio is 5:2. So we want to make sure that each of these, the width to height ratio is close enough to 5:2. And if it isn't, then we're going to throw away that contour. And we also need to check the area. So it shouldn't be too small because then it's probably some noise like this. That's not an actual tape piece. But it shouldn't be too big also. Like, suppose we put our hand in front of the camera, which we do often when we're doing functional checks. The green light reflects off of our hand and we just get this giant green in the image. And we also need to filter that out. So basically we want the area to be a reasonable range for how the area of one of these would look. And then, yeah, we should have a good amount of vertices on these shapes. Like these you would expect at least like 3 or 4. to make a bounding shape around them. And as you can see, like, we're basically filtering out all of these small pieces of noise. They become red here, which means we're just throwing them away. And all of the big tape pieces that we detected are becoming green, which means we actually picked them and we know this is the real tape. Yeah.
For the number of vertices, why aren't they like always 4 for the tape?
And
Yeah,
just to
so-
repeat the question was, why aren't the number of vertices always 4 for the tape?
Yeah, so let's suppose that you can see this isn't a perfect rectangle, right? So it might have even drawn like one line here, and then one line here, but you see how it kind of, it's kind of small image, but it kind of goes up here. So it could have drawn another line here and then like drawn more lines. So basically, if it's not a perfect rectangle, it's gonna like draw as many lines to fit the shape as closely as possible. So that's how it can go.
All of that, like, bounding box fitting sounds like pretty expensive to compute. How do you manage that in like real time on the robot?
Yeah, so the question was that all of this bounding box computing seems pretty expensive, and how do we manage this in our real-time system? And to be honest, so our camera can take 30 hertz images, and our baseline for this vision code is that, okay, we need to run it at 30 hertz, and we are able to run it at 30 hertz with these computations. The most computationally expensive step is the solving, which we'll get to later, for solving for the actual distance. And this stuff is kind of less compared to that. As well as we have another step, which is undistorting our image, and that is also more expensive than this. So yeah, it does seem like it's computationally expensive, but given our 30 hertz goal, which we're able to meet, we are okay with that.
And maybe to add, in particular, the OpenCV routines are pretty optimized, so those run relatively fast. But yeah, I think we have enough compute that we're able to do it.
Yeah. Cool, so now we've found these blobs, but this still might not be completely correct. We have another step just to be fully sure that these are the actual pieces of tape. And one more thing is, you might notice that this was probably part of a real piece of tape, this small one right here, but we still filter that out because it's too small, and that's basically noise. Like, we can't use, it's not reliable to use in an estimate because we didn't get the whole thing. So we're going to go into a bit of background for our next step, and we're going to go over this algorithm called RANSAC, or Random Sample and Consensus. So just to illustrate this concept, just imagine that you're at home, you're going to have guests come over in 30 minutes, and you, for some reason, have to cook dinner, and you've never cooked before. And you need to figure out which combination of spices tastes best together. So what is one way? Let's suppose you want to find 3 spices that taste the best together. Now, obviously, you could try every single combination of 3 spices and taste them and see how it tasted, but that's going to take way, way too long. So just any ideas are fine. How could you find 3 combinations of spices that would taste good together? So yeah.
Maybe test a combination of 2 spices, see which one of those is the best, and then combine that with like another spice and see which one of those is best.
Yeah, you're getting really close to that. So that's very close to what RANSAC is. So here, one idea was just go 5 times and pick 3 spices and see which out of the 5 combinations tasted the best. And that's another way you could do it is you try many combinations of 2, you find one that tastes good, and then you start adding a third one, like what you said. And yeah, so basically you're randomly sampling, because when you're picking your random 3 spices, you're not, each one has an equal chance of being selected, you're not being biased. So it's called random sampling, and you're doing consensus, which is basically trying to see how good they are and finding the best combination. Right, so we apply this algorithm in our next step of filtering blobs, which is basically, if you can see that the centroid, or the center point of each blob, actually fits really nicely on an arc of a circle. So we want to figure out, in this picture we don't have too much noise that hasn't been filtered out. We've already filtered out correctly, but just in case, we want to figure out which combination of these blobs would fit best on a circle, because we would expect that they do pretty well. And you might wonder why we're not doing an ellipse, because that might be more accurate. However, sometimes we only detect 3 points, and you need like 4 or 5 to fit an ellipse of best fit. So yeah, we run a ransack routine, which basically we pick 3 random blobs. So let's say we selected these 3 to start, and we fit the center points on a circle like this. And then we'll go through every other blob. So in this case, the other blob that hasn't been filtered is this one. And we'll see, okay, how closely does this one fit on the circle which these 3 already fit? And if it fits, and basically to see how closely it fits, we will see the distance between its center point and the arc of the circle. And in this case, it's really, really close. So we will do that, and we also make sure, like, we wouldn't expect a blob to be right here on the circle. That just doesn't make sense when you're looking at it. We would expect the tape to project on the top part of the circle. So it would vary a little with distance. If we're farther or closer, these might be like more spread out, but we make sure that they're always in the top 50 degrees of the circle. And yeah, so now we've gone through, we found one combination of 4 blobs. And in the case that we'll do this 15 times, and in this case, like, we've already found the best one, but just in case, suppose there was more noise, we would keep going through and finding different combinations, and then we would pick whichever one we could fit the most, we could add the most to one circle. And that combination of blobs would be the one that we say, okay, this is absolutely sure that this is the tape, and we're going to treat this like that. Does that make sense? Any questions about this slide? Yeah.
How often do you have data that passes step 3 but is still ambiguous, and so step 4 is required?
Yeah, so honestly, I think in a real match we've rarely encountered this, or at least I've never seen it, but we practice outside, and we used to practice in 254's like semi-outdoor field, and there's a lot of noise there. If you have sunlight in the image, it's just going to be like tons of noise, and in that case, often noise does get passed and gets to this step. And there was one case where the robot was actually missing a shot, and restricting the threshold, like, so making it so that they have to be even closer on the same circle, actually fixed the robot's shooting, so it could filter out that extra blob that was not actually part of this. All right, cool. Yeah, so now we filtered the blobs, we know exactly where it is. So we're going to actually figure out where is the robot on the field given these. So another part of background, and this is cost function optimization, and if you familiar with machine learning and gradient descent, you might be familiar with this concept. So imagine that you work at a Tesla factory, and you need to figure out how many cars you should produce in one day to make sure that the cost per car is the minimum. And you have this function, which is, it's not a realistic function, but for this concept, we're just going to use it. And we're just going to assume that if you have this many cars per day in the x-axis, then the y-axis just represents the cost per car. So how can you figure out how you can minimize the cost per car? Because ultimately, this is the minimum cost per car. But how can you find that point? Any ideas? Yeah.
Use the derivative of the function.
Yeah, and specific.
Repeat.
Oh yeah, sorry. He said use the derivative of the function. And do you have any ideas specifically what you would look at in the derivative?
I guess look for it to be 0.
Yeah, exactly. So when the derivative or the slope of the function is 0, then the tangent line would just be horizontal. And you could then find these maxes and mins, and eventually you might get stuck here, say, oh, I think I found the minimum here, but in reality you would find another one right here. And there are 2 ways you could do this. One way is, suppose you have like the actual formula for this function, then you could just use like algebra and calculus and compute the derivative and find that pretty easily. But if you don't have the function, then you have to actually kind of compute the derivative at each step and actually converge towards that point, just using computing. Yeah.
Yeah. So for maybe smaller teams, younger people who don't know how to use calculus, is there a different way you could do that?
Yeah. So actually, I'll show you in the next slide. But our code does not actually use calculus at all. We use a library that does this for us. So yeah. This does not, we did not have to, I didn't know calculus at that point, or not that much of it, but you You don't need to know calculus to write this code, actually. If you understand it conceptually, that's enough. And yeah, so we use a thing called auto differentiation, which obviously our function is not going to be completely like, you can't completely mathematically predict it. I'll get into it a bit later, but it does do some of that kind of trying to find a function and more algebraically compute the derivative. But it's not like completely algebraic because our function is not completely algebraic. So yeah, you compute the derivative and search for minima, as you said. Yeah.
If you're going through all the points, well, why compute the derivative? Might have just like for minimum and maximum.
Oh, why? Oh, if you're going through all the points?
Yeah.
Yeah, so you want to see which way the function is going, and you probably want to chase it when it's going lower.
Okay.
And you can also do another thing where you try random points, and you can, it's called stochastic gradient descent is one word for it, where you try random points and then you see where the minima is. You can do that too. So you're not just going all the way like this through the whole function.
But just to make sure it's clear, we're not actually going through and computing kind of across all the points. There is an auto differentiation that happens in the software tool that we use, Series software.
Yeah.
And that's sparsely set points.
Yeah. But does rely on a derivative to track towards the optimum.
Right.
Yeah. Cool. So yeah, now an overview of what we actually solve for. So the target is symmetric, so we can't actually know, with vision we can't know our exact point on the field. We just know radially where are we around the target. So like if we were 5 meters out here or we were 5 meters out here, we would not know the difference because the target is symmetric. But we would know the distance and we would know the angle that the camera is pointing relative to the target, so the yaw angle. And so we basically solve for the angles of the camera. So roll and pitch are just to detect if the camera is shaking around because our robot's driving really fast. The robot's going to shake around. The camera is going to pitch and roll a bit more, and we would just solve for that. Whereas yaw is really the most important angle in this case, and it's going to be where the camera is aiming. So if this is the target, this is the camera, and we can detect that because we need that to actually aim at the target. And then we also solve for the distance to the target, which is of course going to help us know where we are and tell us how to shoot into the target. And so yeah, we use Google's Series Optimizer to solve this problem. They originally developed this for Google Street View, and yeah, as we were saying, it uses auto differentiation, so it doesn't have to completely do the derivative computationally. Cool. So yeah, we're going to get into this a little more. So we have a few assumptions that help us solve this kind of symmetric problem. We assume that there's a straight line from the camera through the middle tape. So let's say we detected 3 tapes. We're going to assume that there's a line from the camera through the middle tape piece, the middle of that, to the center of the hub horizontally. And the top-down view might make a little more sense, but basically it would go through the camera, through the middle tape piece, through the center. And this doesn't actually have to be true. It could be a little off from the center. But we have found that difference is minor enough that it's okay to make this assumption, and we kind of need to make this assumption to do the computation that we're going to do in the next few slides. And so also we know the hub 3D geometry, so we know that where each of these points is in relation to the bottom of the hub, which we're going to call our origin in this problem, right? Because we know the height of the hub, we know the radius, and we know the angles of each piece of tape. Does that make sense? Cool. So we're going to have to set up this problem by first we're going to find the middle blob, because as I said, we have an assumption that there's a line through the camera, then middle blob, then center of the hub. So we find that by, if we go back to the circle, we're going to find the average angle out of all of these. So the angle would just be, this would just be the angle to each blob. And we're just going to find the average, and then we're going to find, okay, which blob matches the angle of which blob matches the average angle closest. In this case, it would probably be this one, and we would pick that as our center blob. And as you see, the center blob is going to be the most important one for our estimate. Yes.
I didn't see that.
Oh, yes.
There were 4 blobs. How did you pick which of the middle 2 was
Yeah.
center?
So basically, let's suppose our average angle was here, right?
I can't
Oh,
see.
sorry. Can you see
Maybe
that?
if you stepped up over to the right.
Yeah,
and
yeah,
closer
sounds
to
good.
the left.
Sounds good. So let's suppose the average angle was like right over here. All right.
So in between 2 and 3.
Yeah, in between. But it's probably going to be a little closer to 1. And if it's closer to this one, then we'll pick this one.
Okay.
Yeah. Cool. So, yeah, so we're solving for the roll, pitch, yaw, which is the rotation of the camera, and then the distance from the camera to the target. And we have to give initial guesses for these parameters before we converge to the actual estimates. So our camera has these extrinsic matrix, which basically tells us, we know where the center of the robot is, and the camera is mounted somewhere else on the robot. And this is basically a transformation of both distances and rotations to go from the center of the robot on the ground to the camera. And this is basically because the center of the robot on the ground is not angled anywhere, it's flat, but the camera might be angled, might be pitched up, and it might be, hopefully it's not rolled too much, but it could roll a little like this too. And then the yaw, we're just going to initially guess that it's pointing straight at the target, but we'll have to eventually figure out how the camera is actually aimed. And we're just going to guess the distance is 3 meters to start. It's an arbitrary number, but it's like, we might be shooting from 3 meters on the field. But suppose we've already estimated all these in the previous iteration, because we keep running this every 30 hertz. Then we would just start at the previous estimates. Suppose we found out that we were 2 meters away from the target. Then the next time we go to solve the distance, we would keep it at 2 meters and solve again, because that would definitely decrease the computational intensity. And now we can't just let these go forever. Like, we know the distance is never going to be like 20 meters, right? That's not possible. So we constrain all these parameters. The camera really shouldn't be shaking that much. So we constrain the roll and pitch to be pretty close to how the camera is actually mounted, those angles. And the yaw, the camera if it's seeing the target, it has a 90-degree field of view around. So we make sure that the yaw cannot diverge from the being pointed straight by more than its field of view, because that would just be physically impossible. Yeah.
For example, if the yaw is like too far out from the camera vision,
Yeah.
you just set it to like say 90 degrees, or like how do you correct for that?
Yeah, so you'll see in a bit.
Maybe to repeat the question.
Oh, sorry, yeah. So the question was, when the yaw is too far out, when the camera is actually pointed away from the target, how do we indicate that in the code? What is the actual value for the yaw?
Or at least if it returns, or if it says that it's too far out,
Okay.
even though it might not be.
Yeah, so or if it says that it's too far out, even though the camera is not. So actually, it's impossible for the solver to go past this field of view, even if it is. So that means that, yeah, suppose the camera is pointed away from the target, and then we say it's pointed straight at the target. We have another part of this message called a confidence, which tells us how good our estimate is. And in that case, the confidence would just be 0. So we would not even pay attention to that estimate at all.
I see.
Yeah.
You have this code running on each of the 4?
Yeah, so all of the stuff that I've gone over so far, each Raspberry Pi is running this independently.
Okay. And then are you going to talk later about how you choose between the signal that's coming from each of the Pis?
Yeah, I can like go a little over that, but there's going to be another talk which is going to be, yeah, the IMU talk is going to be
localizer talk later that talks about
that's
how to
going to
fuse
go
the data.
really deep into that. So yeah, so we're going to constrain, and then we're just going to constrain the distance to be something that we would actually see. If we go more than 10 meters, like, we're not going to actually see the target very well, so that shouldn't be possible. And then if we go closer than 1 meters, the target is going to be way too high angled up, so we're not going to see it either. And yeah, these are not like actually calculated numbers, these are just reasonable numbers. And yeah. So we're going to go onto our cost function. So just like the cost function for the price of Teslas per day, this is going to be our cost function, which tells us how close our estimate is to the actual estimate, to the actual positions of the hub. So we're going to be given the current estimate of all our values, which would just be the initial guesses to start. and we need to tell series how good this estimate is. So how closely it matches the actual pieces of tape that we detected. And that's called, the residual is just the error, which is how off our estimate is. So to start, we're going to compute the hub camera transformation matrix. And this is basically, it's the rotation and translation of the hub in the camera's frame. So if you're the camera here and the hub is here, but let's suppose the camera is rotated, then the camera will think that the hub is rotated. This is going to be in 3D, so the distance would just be pointing straight at the hub because, as we said earlier, we have the assumption that the camera is pointing straight through the middle tape piece and to the hub. And then the rotation would just be if the camera is rotated to the side. So this is just using the current estimate of our angles and distance. We just make this matrix, and if you're interested in that, you can look at our code. And we use, this heavily utilized on our straight line assumption. And now we're going to project the 3D tape points onto the image. So basically, we have our circle of the target, and we know the transformation between the camera and the hub origin, which is right here. And now we know the points, we know these points, these tape points relative to the hub origin. So we can combine those two things and actually put these tape points relative to the camera. So we take these 3D tape points, which is the center of the tape, in the reference frame of the hub, so relative to the hub, and then we use this transformation matrix using the angles and distances to go to how far these points are and how these points are angled relative to the camera. And then we use another matrix, which is called the intrinsics. And the function of the intrinsics is basically, you have a point in 3D space from the camera, and you want to project that onto the image. So let's say I'm looking at you. If I was a camera, what pixel would you be on? So the intrinsics matrix has some internal values on the camera that will convert a 3D space point into the image, into the pixel in the image that it would project to. And then we can convert this 3D point of each piece of tape into where it'll project onto the image. Does that make sense? Any questions about that?
Are your intrinsics taking into account optical distortion, like barrel distortion or pincushion, or?
Yeah, so we do have distortion coefficients that we actually use separately. So this step doesn't take that into account, but the first thing we do after we get our image is we use OpenCV to undistort the image.
But to your question also, the camera intrinsics, so it's just using focal length and image center at this point. Right. Yeah.
And sorry, his question was if we take into account distortion in our intrinsics here. All right, any other questions on this slide? Yeah, Phil?
You say you need to tell series how off this estimate is. How do you know how off the estimate is?
Yeah, so
I missed that part, I think.
yeah, so I haven't gone over that. That's going to be the next slide.
Oh,
actually.
I see.
Yeah.
Sorry, and just the question is, how do you tell series how far the estimate off is? But we'll get to it in just a second, what the residual is.
Yeah. All right, so this is the part where we will actually compute the error and the residual. So we're going to have two parts to our error for how good our estimate is. One is going to be the location error. So we detected a bunch of these, the green is what we detected. We detected a bunch of these points, right? With filtering green and then our ransack and other filtering steps. Now we also have projected tape points from our estimate of angle and distance. So these should match up. So we're just going to compare the center points of both of these blobs, the detected one as well as the estimated one. And these should be close together, so the difference between the x and y of those centers is going to be part of the error. And yeah, this is going to help the solver, this is going to help the solver solve for the location. And yeah, so the other part of our error is the size error. So I said that the middle blob was important, and basically the middle blob is usually going to be a better detection. Like you see how this one, it's on the side, so it's smaller, it's kind of angled more. It's not going to be as good, as reliable of an estimate. Whereas the middle one, in this case it might be this or this, the size of those are pretty good from what they actually should be. So we projected a bunch of tape points using our transformation, And we're going to compare the projected image size of those to the size of this, let's suppose this is the middle blob, of this middle blob. And we're going to use that also to figure out how good our estimate is. That's going to be the size error of our estimate. And the solver is going to keep running. We're going to keep giving it errors. It's going to keep updating the estimates to try to reduce this error and eventually converge to the lowest error possible, hopefully. So here you can see that this white bar is our estimate of the tape of the hub, and these center points are the center points of the tape pieces that we're estimating. And here you can see the solver is trying to reduce both of these errors, and it's changing the estimate of rotation and distance so that what we think the hub is exactly or very, very close to where the hub actually is. Does that make sense to everyone? Any questions on this? Right, cool. So now, as you were saying earlier, how do we differentiate from actually good estimates and bad ones? So we have this confidence message which will tell us how good our estimate of rotation and distance was. And basically, so we have the size error, or sorry, location error, which was telling us how close our estimates were to the actual locations of the points. And we're going to actually, sorry, this should say location error, but we're going to compute the standard deviation of those points. So we have many of these location errors, and we're going to just compute the standard deviation to kind of get an, it's not exactly an average of those, but it's a different way to get an overall error from each of those location errors. And that's just going to tell us, okay, overall, how good are we doing on matching up the positions? And that's going to be converted into our confidence. So the reason we do not use the size error for our confidence is because that is relatively higher, relatively usually much higher compared to the location error. And we added the size error later, so we just wanted to keep the confidence just at the location error. And the way we convert this standard deviation, which is in the units of pixels, so it's a nice way to see how good we're doing, into a confidence message. And our confidence is going to be from 0 to 1. So how good was this estimate? Is we use this sigmoid function, which is it's a function which involves some exponential, and it's a nice curve. And in this case, so we give it 3 points. We say, okay, if we had 0 standard deviation in pixels, if we had no size error, then obviously our confidence should be 1. That's like as good as we're going to get. If we had, then the next two values are kind of tuned. Like we found out, like we're usually getting a bit lower than 1 standard deviation in 1 pixel. So we're going to say, okay, that's a pretty good estimate. We're going to say that's 0.95 confidence. But we would still accept something lower. Maybe if it's a standard deviation of 3 pixels, so if we're usually off by like 3 pixels in location, then we'll say we're 75% confidence. And the way we use this, we were thinking of doing something like more detailed with this confidence message to weight these measurements, but what we ended up doing is just, if it's below 0.75, we throw the estimate away and we don't use it. And that's worked just fine, because usually it's, as I said, usually it's below 1 pixel in standard deviation. And this is just an idea for the curve that converts standard deviation to confidence. You can see here's 1, and it's 0 pixels at 1 confidence, and then it just goes down after. Yeah, does that make sense? Cool. So now, this is the last step. We have to send these results to the localizer, which is going to fuse, because we have 4 Raspberry Pis, which are each measuring where the target is, and we have to now figure out where is the robot actually. So we're going to send the yaw, distance, and confidence that we determined from our solving is going to be sent, and yaw is just the horizontal angle, is going to be sent to the localizer. And the localizer, if it sees this confidence is below 0.75, it's just going to throw away these two like it's a bad estimate. And you might notice that, hey, we also solved for the 2 other angles, the pitch and roll. Why are we not sending those to the localizer? And the reason is we don't actually care how much the cameras are shaking to figure out where the robot is. The reason we solve for those is because this yaw and distance could be getting messed up if we have a wrong value for that's because of the camera shaking. So we need to account for that camera shaking by figuring out the roll and pitch. and that way we get a more accurate estimate for the yaw and distance. And yeah, so we're going to send this information to the localizer, and it's going to figure out where the robot is, merging all 4 cameras' estimates with a common filter. And if you're interested in that, James is going to have a talk on that in a bit. And yeah, I'd highly recommend that one too. So this is all for the 2022 vision, but we're going to go a little more into our results. So we honestly did not expect it to be this accurate when we started. Because we just thought, oh, the tape is not going to be super reliable. These cameras, the reflection of the tape is not going to be this reliable. But through all these filtering steps, and I think definitely the solver was the big part, we've actually got it to be super reliable. So this is not like some perfect statistics. This is just like observations that we'll take the robot out. It'll be far, like even at 6 meters, and it'll be the estimates of vision will only be off by a few centimeters. This is of course like stationary. When it's moving, it's going to be much less accurate, but when it's still going to be pretty good. But when it's stationary, it's really, really good. Yeah, so this is our 2022 vision, and hopefully this video of the robot doing its autonomous makes a little more sense on how the robot is actually able to aim at this target. Because once we know where the target is, that's how we're going to aim into it. So yeah, now we're going to just look at a little preview of our next year's vision. So as some of you guys might know, first is going to put April tags on the field, which is going to be really good because we honestly kind of hated having LEDs. They're super bright, they're annoying, just another thing you have to deal with. And so we're going to use these April tags, definitely only these, and no LEDs. And so we're going to have 2 steps for our process. We don't trust that they're going to put these in the same place or same exact place on every field. And if we have a practice field, it's definitely not going to be placed perfectly. So we're going to have a mapping process that's basically, we're going to put the robot on a field, we're going to take it around, it's going to take a bunch of pictures of these tags that are placed around the field, and it's going to figure out in the location of each of these tags using a kind of SLAM problem. And then, now when we're in a match, we have this map of where each one of these is, and we are going to localize off of it to figure out where the robot is. Okay, Phil, yeah.
Do you actually get to drive around a competition field?
Yeah, so we have a calibration process, so we'll just have the robot on and we'll have to drag it around. We'll have to,
before a match.
yeah,
so we won't be able to drive it, but we'll be able to move it around.
yeah,
I see, okay.
Do the robot around.
yeah, we're allowed to have it
During
on, just not
practice.
enable it in that time. Yeah. And this is also using series. We're currently developing this software right now and testing it.
So for the calibration, does that need to be done before every match or before every game?
So before, actually one time in every arena, I guess.
That's what I meant.
Yeah.
Like during the dedicated calibration.
Yeah, exactly. So we do that. This year we had to tune our exposure for the light at every new field because the lighting is different. So the analogous thing next year would be just, we go to every new field, we build a map for it, and hopefully like next time we come back to that field, we don't have to do it again. Cool, and yeah, we were doing some preliminary testing right over there. And here are some April tags that we were localizing off of. And another thing we were doing testing is our Charuco diamond tags. And Jim is going to talk a little bit about how we calibrate our extrinsics. If you remember, our extrinsics were telling us where the camera is relative to the ground or the center of the robot, which gave us our initial guesses for our roll and pitch.
Cool, thanks. Thanks, Milind. So yeah, we just want to give kind of a preview into some work we've been doing, also with Austin Shu on extrinsic camera calibration. I'll talk a little bit more what I mean by that. So camera calibration, we roughly break into 2 pieces. Intrinsic calibration being the internal parts of the camera and the lens assembly. So it tells you kind of where the camera is centered, the focal length of the camera, any distortions that might be in the camera. So we have a process we use for doing intrinsic camera calibration. I talked about that, I think, the last Spartan series, so there's notes on that. Extrinsic calibration is really about where the camera is in the world relative to some other reference frame. It could be another camera if you've got stereo. It could be, and what we care about here is where's the camera related to the robot center reference frame. So we use the IMU actually in the Spartan board and the Robo Rio as kind of our robot reference frame. And so the extrinsic calibration is going to be the rotation and translation from that robot reference frame to where the camera is. And of course, that's really critical because all these measurements we're taking, like Milind just described, are in the camera frame. We know where the targets are or the April tags for next year in the reference frame of the camera, but that doesn't tell us where the robot is. It just tells us where the camera is. So having the extrinsics allows us to map from where the camera thinks it is to where the robot should think it is. So there's kind of this extra step that you always have, that we have to take information that's from the camera and map it to where the robot is. And that's the extrinsics. So it's just a simple transformation, of rotation and translation. This just describes more of that same thing. It's kind of this map, which is rotation and translation, that takes you from the robot origin to the camera frame. You can think of it as a transformation between frames. So it's kind of how does the camera rotate and translate in space. It also tells you how a point that was seen in the camera in 3D would map into the origin frame. So that's just another viewpoint of it. But this is what we'll use to figure out where the robot is in space by kind of taking that observation. And just real quickly, I'll talk about our approach. As Milind mentioned, we're using a known target like the Truco diamond board that he showed, and I'll show a picture of it in just a second. So a known target that we can get 3D information from. So these targets we know the size of the target, we can figure out where corners are, enough to compute where the camera is relative to that target. So then we'll record camera observations and from that target, and we also record the IMU data of the robot as it's moved around. And so this is one of the things, the process that we use is move the robot around in space. As it's moving, it's detecting the target and figuring out where it's moving based on the target, but also the IMU is giving it spatial motion, understanding where it moves in space. Again, we're using the series solver to both to estimate two critical things. One is the extrinsics, so where's the camera with respect to the robot center or with respect to the IMU. So that's the camera extrinsics. And we also use it to give an estimate of where the target is in space. So if we know kind of where the target is in space and the map between the camera and the robot, then we can kind of understand the relationship between the target and the camera. And we use that as in our solver. So we've got those two pieces of information are the things we're trying to solve for, the things we're trying to estimate. The way we solve it is kind of interesting. It's this fun little trick that is similar. There's this software library called Calibre that does similar things. But essentially, you take the IMU and kind of play the position and orientation of the robot forward as it's moving around, and you fuse that with the camera data, the camera observations using a Kalman filter, and you look at how far off each of your camera observations is from your estimate. And so that's your error. Milind was talking about your error, your residual. So you compute that for these two things that we're trying to solve for, the location of the camera with respect to the robot and the location of the target. And then each iteration of the solver is basically adjusting where it thinks the camera is, where the extrinsics are, and where it thinks the target is. And so it kind of tries each time, just like we did with the solver for the target in the hub, it tries each time to adjust that so that your whole solution of the motion of the camera has minimal error. So it minimizes the error off of that. And maybe just to show a little bit what this looks like. Again, we're kind of still working on this, still nailing down the final pieces of it, but we hope to have it solved pretty soon. This is the camera view of the target, this Truco diamond target. Oh, sorry, thank you. The camera view of the Truco diamond target as the robot moves around. I'll play it again. And on the left is the raw camera video. One of the things we found was that our camera is a bit fuzzy. I think there's some issues actually with the assembly of the camera, so that we had to do some thresholding to binarize the image and make it more usable. And on the right, what we have is the estimate of the location of the target. You see it's pretty stable. These three axes, red, green, blue, are the estimate of the orientation of the target with respect to the camera as it tracks through the world. So it's able to track this target in space, in 3D, and then as the robot's moving, we again have the IMU data that tells the robot motion, and we kind of bring those two together to figure out where the camera is relative to the robot center, the IMU basically. And what this looks like, another visualization for this is, right now, this is going to be where the robot thinks the IMU center is, where it thinks the camera is relative to the IMU, and where it thinks the board is relative to that. So this is just kind of another visualization of these different reference frames. So you can see as we're moving around, the board should basically stay in place as the robot, both the IMU and the camera, move around relative to each other. And so this is kind of the result of that solver. I'll play it one more time because it goes a little fast. This is a result of that solving that I mentioned to figure out where the camera is relative to the robot center, and then where the board is. The center of this image would actually be where the board estimate is supposed to be. But we're able to solve the extrinsics for the camera by doing this just simple manipulation.
So it looks like the camera and the robot center are changing a little bit.
Yes.
I mean, is there a change, or is that just computational?
Sorry, there is not a physical change. If that's, so the robot relative to the camera is not physically changing, no, but that is a computational artifact, yeah.
Gotcha.
Yeah, so that's right. It will change slightly over time. Ideally, not much, but this is, because what this is essentially is playing forward is that IMU data fused with the observations. So as that goes through space, it will adjust itself slightly. And that's it. Yeah, so questions, yes.
Yeah. So I was wondering, my question is kind of twofold. So how many resources did you need to devote to vision to get this working? I.e., like how many people and how much time?
Mm-hmm.
And for a much smaller team like my team, like what would be an achievable goal and how to get there with maybe 3 or 4 people working to get all the code for the robot working?
So to repeat the question is kind of how many resources did we need to do all this, and what's an achievable goal for a small team that maybe doesn't have some of those resources? Yeah. Do you want to start with that?
Sure, yes. So we had you and Yash, right?
Yeah.
Yeah, so we had 3 people working on it, but we devoted the majority of I'd say until March, working on, and even after, so until like February, March was like developing this process. We spent like all the time on this vision, most of the time. And then after that, it was like we have the code developed, but there were many bugs, or there were major bugs that we hadn't found until later. So we had to do a lot of, in addition to just writing this code, you have to do a lot of taking pictures and running it through your code and figuring out the problems.
And I think, so there's basically 3 people working on this. Like I mentioned, Austin also was involved in some of this optimization work for the extrinsics. I think, so if I look at the intrinsics and extrinsics, the code we have obviously is published, so you're welcome to use that. And it's in kind of functional libraries, so it should be usable. Don't quote me on that, but it should be usable without too much effort. You would need some of the boards, and those can be printed out to be able to do that for the intrinsics and extrinsics. Now, I talked about it last time, the last Spartan series, about the intrinsics, and it's also true of the extrinsics, is you can just use kind of default numbers. Your camera, it's easy enough to compute what the intrinsics should be for a camera based on the lens and your imager size and things like that. The extrinsics, you could take it from CAD. You've got a CAD model, or you can take a tape measure, and the angles are always a little bit trickier to find out and get good results from, but if you have that information, you can just use that, right? So this is much more elaborate than it has to be, and we're trying to just pin down that last little, extra few degrees and extra centimeter of accuracy. Especially in rotation, those degrees matter very often. You can imagine being slightly off in a heading when something's 4 or 5 meters out makes a pretty big difference in the distance that you're off on that target. So you don't need necessarily the intrinsics and extrinsics. In terms of the optimization, there's going to be lots of different shortcuts you can take to not have to solve a full optimizer. But I think at the end of the day, it's just kind of how far you want to, how accurately you want to get your solutions.
Like in the beginning, we tried, like, instead of doing this whole optimization process, we started off with just a reverse. So here we were projecting points from 3D to 2D. We tried a reverse projection from 2D to 3D, which it was not very accurate, but I mean, maybe if we spent more time on that, if we didn't want to do this full optimization process, we could have gotten that. And also, like, we did so many filtering steps, you could have definitely bypassed some of those steps. Like, you could have just filtered off of color and size to figure out which ones were the blobs, and most of the time, like as I said, on actual fields, that would work most of the time.
I should also mention we are leveraging James Kushmal, who's talking this afternoon about localization, all the localizer code also, right? So we're handing off this observation or this measurement of where we think the robot is, but it's not a full estimate. It's just the distance and yaw, or head distance and heading to the target. He's got to then incorporate that into estimates of where the robot is based on the IMU, based on the wheel encoders and things like that. So we are leveraging quite a bit of extra work there. Also, make sure to call out, we're leveraging the camera, all the work that was done to do the camera calibration and manufacturing, assembly. The lighting board electronics was developed. There was 2 or 3 people that worked on the electronics for the lighting board. So, I do want to be cognizant of the fact that there's a small group of people working on just that software piece, but there's a larger group that's making the whole vision system work. Yeah.
Could we get the URL for this presentation?
Yeah, sure.
I don't know how to.
Well, I can put it in our. I'll put it in our README in that folder in our code, and I can link our code right now.
Yeah.
Does that sound good?
Yeah, that's fine.
Right.
Because I'm not sure how to get you a URL. It's a Google spreadsheet, so.
I'll just give you the place in our GitHub where it'll be, and I'll link it right there after.
Yes.
Do you know how many people were involved, or like how much effort was spent on the hardware side for the Raspberry Pi?
Let's make sure this one works.
So how much effort was put on the hardware side for the Raspberry Pi, LEDs, and then of course there was a 3D printed enclosure that helped carry that. The Raspberry Pis, I did some of that work. We had, Henry helped out. So there's probably 2 people that were helping get the compute up and running and the cameras up and running. The LED board, I think, was a total of 3, two students and a mentor working on the LED board, both design and assembly. The CAD, there was 1 student who did most of the CAD modeling for this assembly that basically allowed us to rigidly mount the camera and LED board together on a block with a Pi, so it was kind of all one block, and then that could be mounted on the robot as an assembly. So that was actually a nice 3D structure that we print out specifically for this competition, for the particular tilt that we wanted. That was another thing we had to figure out, was kind of how much tilt do you want to have on the robot based on where it's located, so that you maximize your chance of seeing the target. So you wanted to be able to see the target very close, within a meter, but also, so you had to be up close, you need to be able to see high, because the target's up high, and then further away it's lower in your vision, and so being able to see things far away. Yes?
What are your thoughts on COTS or open source options like Limelight or Photon Vision right now?
Yeah, I don't have a ton of thoughts on Limelight or other off-the-shelf kind of tools. We've kind of chosen to go the route of building our own, so that we have more control. We can kind of really tune it. What we've heard from other teams is often a feeling of frustration. That it doesn't do exactly what you want, or you're not getting the results you want out of it. At the same time, going back to resources, if you don't have all the resources, which we're lucky to have, to be able to build these things ourselves, then it's a great solution, right? So it makes perfect sense. And some of it's just a question also of how low can you get in the stack to be able to pull in the data that you need, right? If you're getting a full image out of it and being able to optimize and do everything that you want, then that's great. But again, I've heard some frustration, and I think this may be more a 971 approach, is like, let's build all the things we can and control our fate basically by building the components ourselves. And I think the same thing, it's kind of setting us up for the April tags, being able to leverage those, right? We already have a lot of compute infrastructure for dealing with Chiruko targets or Ruko targets, April tag type targets, these QR looking code targets. Just kind of building on top of those. And I do want to call out, OpenCV has a ton of libraries there that we leverage. So we're not building most of this from scratch. Between OpenCV and the series solver, I think we've gotten quite a bit of leverage. Yeah.
So you guys have like 3-4 people working on the vision side of the robot. How many people do you guys have working on the robot part, the robot actual code?
So the question is, if we've got 3 or 4 people working on the vision side, how many do we have working on the robot?
So on the code?
Oh, the robot code.
So we
software side still. Okay.
We probably on this robot we had at least 10 people working on the code, and maybe even a little more. But the way we had was that we had a lot of new members last year. So for our subsystems, we have like a lot of subsystem libraries. So just to teach them how our code works, we had them work in groups. Do collaborative coding. VS Code has like collaborative coding feature, and they would code those subsystems together. So we were able to get a lot of people to learn from that. And then for then more newer things like our localizer, vision, and catapult code, we had just like Austin, who's one of our lead mentors, worked on the catapult code. Then James Kuzmal, who's going to be doing the next presentation, worked on the localizer. And then me, Jim, and then one other student worked on the vision code.
So your robot code and vision code are working simultaneously?
Yeah, basically. So we were just like we would help the people who are working on the robot code, the newer members, but we would also simultaneously be developing this. And I think that was really nice to have this year. Yeah.
And maybe just to call out some of the other software aspects that the team works on, there is a group that was working on the autonomy code, so working on the autonomous, basically how do you kind of draw autonomous routes and visualize all of that and then implement it. And then also a group that was working on scouting. We have built a scouting app that we leverage.
Yeah.
Do you also use the cameras for the drive station, or with it?
Yeah. So
tuned so extremely for exposure.
Right. The question is, do we use the cameras for the drive station?
We have a separate. We have 6 Raspberry Pis. So we have 4 for vision, then 1 more for our IMU, which is going to fuse those vision. And then we have a 6th one, which is a logger Pi, which it logs all these estimates. It also has a wide-angle lens that is normal exposure camera that's just in the middle of a robot, and it has 2 functions. One is our driver camera, so they can see that, and it also it detects ball color too, and so we just spit out the ball if it's the wrong color as well with that camera.
But it is one of the drawbacks of, at least in my mind, of the reflective tape, because you have to turn the exposure down so low, the time so low, you really can't see anything else.
Are you thinking about streamlining that with April tags or TBD?
You mean in terms of the number of cameras we would use? Probably, yeah. I mean, I certainly would like to be able to leverage the same cameras to do anything. We're not having separate camera to do our driver station.
Yeah, definitely.
Yeah.
So you're getting all the raw and distance on the Raspberry Pi. How do you get that to the robot?
Yes.
The Rio?
So the question was, how do we get the raw yaw distances that we computed here to the RoboRio? And so first, it's going to go from these 4 Vision Raspberry Pis to our IMU Pi, which is our localizer. It's going to fuse all these together in a Kalman filter. And as we said, James is going to be talking about this. And then this localizer is just going to prepare a flat X, Y, and yaw estimate, and it's going to send that in a message to the RoboRio. And our software, we actually have an infrastructural layer of software called AOS, which is open source, and it's primarily for communicating between processes and different computers too.
So it's basically message passing over Ethernet connections between the.
Is there a reason to use like the network cables infrastructure?
Sorry, can you repeat that?
The network cables, like RoboRio has its own network cable, and you can like connect the Pis to the clients, and that was what I was thinking we would do that for our robot. I was just wondering if you guys, there was a reason or the problem you guys would use that.
I'm not familiar with the RoboRio network cable setup. I think we wanted to again, leverage some of the software that's already been built, or especially around logging data. So we again, control kind of where everything's going and the timing of it, the ability to make connections how we wanted. But yeah, that's where the path that the team has gone. Yeah. Any last minute questions? I think we're right at time.
Are you running, it sounds like you're running most of the code on the Pies versus on the RoboRio itself? Or?
So the question is, are we running most of the code on the Pies versus the RoboRio? All the vision code is on the Pies. And then the localization code, robot control code will be on the RoboRio.
Oh.
Yeah. So, but just the vision piece. So it's almost, think about vision is purely just on the Pi, because each one is driving its own camera, and it does the full computation and sends a message over to the RoboRio.
So the Pi that you're using for the localizer communicates with the RoboRio?
Yes.
The final?
And then the final data, yeah, so it communicates with the RoboRio, and the final data fusion is done on the RoboRio. And then, excuse me, as Milind mentioned, there's a logging Pi also that can listen to all the different Pies and the RoboRio and fuse, log that data, bring it all together.
Yeah. Cool. And just to reiterate, so if you go to our GitHub link, and then you go to this folder, Y2022/vision, the README in that folder right after this, I'm going to post the link to the slides. So,
Yep. I think they may post the links to the slides at some point also, but after the fact. Yeah. All right. Thanks very much.
Thank you.